How do we know if the brain is doing a good job? Well, this is a conference on neuromorphic engineering, and so I figured to start, I will give you a little demonstration network of the kind of principles that I'm interested in talking about here. This will be a network that can classify objects. It can generalize to different scalings and rotations. It does tend to favor symmetrical representations. It has an evolved sense of what we might call beauty, and it's really agitated about being stuck in a box. I'm just kidding. I'm not going to talk about these things. But this is where we'd like to go. We'd like to have something that is agitated about being stuck in a box. What I'm going to tell you about today is a tool that I think would be useful in understanding when do we know that we're capturing what the brain is doing. And so the premise here is that I'm thinking primarily about early sensory perception, things where the information about a scene is distributed across many neurons. So it's a distributed representation. And the key here is that it's a nonlinear distributed representation. And so I'm going to talk about a tool that can tell how efficiently a brain is extracting information about this, about your sensory percepts. So I'm really interested in nonlinear computation. I think all interesting computation is nonlinear computation. If it weren't, then you wouldn't need a brain. You could just wire your eyes to your hands. And perception has to take a tangled manifold of stimuli and untangle them so that with simple neural operations, it can tell the difference between apples and oranges. So all of us know from a lot of the work in deep learning and Sobenko theorem and all of these things that the idea of nonlinear computation is powerful. Let's say we're trying to distinguish yellow from blue dots. If we want to just draw a single straight line, we can do that. But now if I give you these yellow and blue dots, now there's no straight line that can do that until we embed nonlinearly in high dimensions, and then we have this nice straight line that we can draw there, making the problem tractable. So a classic example of this, in fact this is the example that killed perceptrons for many years, is the XOR problem. So you have two variables x and y, they're both binary, and you want to be able to pull out if just one of them is active. And the usual way of thinking about this is that the deterministic view, you have some nonlinear function of x and y, and this is the thing that tells you about z. That's how x and y encode z. I'm going to offer a different perspective, maybe controversial, maybe not for many, but it's a statistical view, and that is that, and I think that this is really a more useful view for thinking about distributed codes like in the brain and natural tasks. And that is that the information about z is contained in noise correlations between these variables x and y. So if we care about z, and we don't care about whether x is 0 or 1, it might fluctuate from trial to trial, or image to image, or task to task. And y might do the same thing, fluctuating back and forth. And we don't care about what the value of y is or x is. We just care about whether they're the same or different. So that's noise correlations viewed given z. So my definition of noise is anything you don't want to hear, maybe this talk. This includes all sorts of different things. There's internal noise, stochastic variability, chaotic dynamics, internal network states. And then I think the more interesting stuff here is the external noise, nuisance variables, task irrelevant variables, things that influence what you're seeing but are not relevant for the task. So if you have this kind of noise, I think that the natural way to solve problems and think about what the brain is computing is in terms of inference. So we might have some kind of simple graphical model or a complex graphical model, and you might want to do structure learning on that graphical model in order to pick out some of the more abstract kind of features along the lines of what Gary was just talking about. And we have methods where we can take that graphical model and consider probability distributions, which are the embodiment of those graphical model nodes, and embed them and represent them in terms of neurons. And the key here is that you, again, need some kind of nonlinear computation in order to do inference here. This is not what I'm going to talk about, but this is fun stuff to talk about. So if anyone else wants to talk about it later, I'm delighted. What I'm going to talk about here is more generic nonlinear computation. And in particular, I'm going to take a really, unfortunately, simple view in the sense that it's going to be a feed-forward architecture. But we have notions of how to extend this to recurrent architectures, which we think are also very important. So the usual way that people think about population codes, by far the dominant way that people think about this, is in terms of what I'll call linear population codes. So you have some stimulus S, it generates responses R, and then somehow the brain generates some behaviors by decoding those Rs. And the fact that the relevant aspects of the behavior and the stimulus are encoded in the mean responses, this is what is going to make it a linear population code. And what we have to think about in terms of judging the quality of what the brain is doing is a nonlinear population code where the information is not yet accessible in this little R, but it has to be transformed in several stages before it gets to something where it's actually linearly decodable. So first, just a simple way of describing a linear population code so we can leverage that. You have some neural response, you have a stimulus, you find in the brain that your neurons are tuned to the stimulus. They change their mean response. And if you picked one stimulus, you get some response. If you have a different neuron, you'll get a different response because it has a different tuning curve. And so if you take the mean responses of all these guys, you'll get some mean population response as a function of, let's say, neuron number. And if you change the stimulus, you'll change what your population response is, and that's how the brain knows what you're seeing. We can think about this, I think it's fruitful to think about it in a high-dimensional neural representation. So here each axis is the activity of some neuron, and the stimulus now traces out this one scalar stimulus, for example, traces out some line as the mean response of the population as a function of S. And let's say our task for some animal that's doing this task is to figure out whether it was stimulus 1 or 2, the red or the green dots. Of course, the brain doesn't have color in the brain, but nor does it get the mean response every time. So from trial to trial, you'll get variability, and this we characterize as some noise, and we can describe its covariance as one statistic that explains the distribution of possible responses. And if you have a different stimulus, you get a different noise distribution, and that might be partially overlapping. And the fact that it's overlapping is what makes us confused, right? That's what makes these tasks hard. So for the linear population code, we're just going to read this stuff out as a linear sum, just a dot product between some template W and your neural activity R. And that will give you some estimate of the stimulus, and then you can say, is that plus or minus? This is just a perceptron, right? In a linear population code, all the information about a stimulus can be extracted locally as that linear function. And when that's true, then that means that your likelihood is described by the exponential family with linear sufficient statistics. You see this R shows up in the exponent there. And another way to say this is that all of the Fisher information, all the local discriminability information is linear Fisher information. So the readout here would be there's some signal direction if you're trying to discriminate between these 2 points. And the signal goes in that direction. And the readout might be in some other direction. And so when you read out, you project not just the mean signal, but also the noise. And the width of the noise projected onto that readout direction, that I'll call theta, and that's some threshold. That tells you how big does the change in stimulus have to be before you can beat the noise. And that's when you can tell the difference between 2 things. Right? That's a population threshold based on this linear readout. Now, if you picked out a different readout, you might do better because you're picking out the narrower part of the noise distribution. Now, if you have these different readouts, each different readout will have a different projection of the noise, and that projection will make it all the way to the behavior. And so we can learn about that readout by looking at the correlations between individual neurons and the behavior. Which parts of the neural fluctuations made it out to the behavior to change the behavior? So we can do that by calculating the correlation coefficient between the behavior, which is this S hat, and the responsive neuron K. And if we just do a little bit of math, we get this expression which depends on the covariance of the noise and the readout direction. And this is actually just a simpler version of what Hefner published in last year. Interesting study there. So we're going to generalize that. But first, let me just mention that where does this expression come from? Well, if you're correlating the behavior S hat with some neuron, and we remember that S hat is the decoded population, then we just substitute that in. We see that you get a decoded covariance. And so that's where this QW comes from. It's just helpful to think about. Now, how do we know when the brain is doing a good job? Well, that for me means that it's extracting all of the information that it can about the stimulus of interest, And here, if you're doing a linear decoder, the optimal linear decoder removes the noise by inverting the covariance. Okay? And now if you take that choice correlation that I described before and you plug in this W, this optimal W, the removal of the noise cancels the noise as it's designed to, and you end up with something that's just dependent on single neuron properties. In fact, this expression can be described as the threshold for one neuron. And the proportionality is the threshold for the whole population. So when you're doing optimal decoding, the choice correlation is the ratio of population to neural thresholds. If we think about this in terms of information, the correlation that a neuron has with behavior is just how much of the information does it have? What fraction of information does it have? And so if it has good information, it predicts the choices better. And when we actually apply this test, which I emphasize is just a single neuron at a time, we can evaluate the quality of the whole population, the decoding of everything, in terms of one neuron at a time, making a bunch of independent measurements. And when we do this in monkeys, we find that it's a pretty good description of the relationship between the choice correlation and this prediction of optimal decoding. So I'm not going to talk about that further, but just to say this is the kind of test that you can actually apply to real data. Now that's a linear code. And you might expect a linear code if you're close to the decision. You say, okay, I have this recorded area, and the choice is driven by that area, so the readout is maybe naturally described as a linear combination of those neurons. But that's not what we're really interested in. We're interested in how the brain comes to this information, how it gets that information. We might be recording from some earlier area, and that information goes through some complex nonlinear transformation before it gets here. So if we're recording here, we might not expect to see any linear information at all if there are these nuisance variables. For example, if you have some variable and you multiply it by something which is equally likely to be plus and minus, you wipe out all of the linear correlation, right? You end up with just 0 on average. So you're going to do this measurement, you'll find nothing, and you say, okay, well, does that mean that there's no information here in the brain? No, you have to account for the fact that it's nonlinear. Here's how we can account for it. Okay, so I described to you the linear population code. The generalization to a nonlinear population code is pretty straightforward. Instead of being a decoding of R, it's a decoding of R. But now it's capital R, which is the sufficient statistics for the more complex nonlinear encoded information. Okay, and I'll describe where this would come from. But once you have that family, this exponential family with nonlinear sufficient statistics, then you can describe all the information as being nonlinear Fisher information. It's the same formalism, just thinking about it from the downstream perspective effectively. Now I'm going to specialize just for concreteness on a quadratic code. And we have a bunch of different examples where we might think in vision, audition, or balance, where you might expect to find something like a quadratic code. In vision you have a product of reflectance and lighting, which gives you your image. Right? So these guys that's kind of a quadratic code there. In audition, we think about sound localization as arising from quadratic. You're measuring correlations between signals from your left ear and your right ear. And that correlation is, of course, a product as well in the vestibular system. If I tilt my head, then gravity points in a different direction. But it could be that my head is straight, but I'm shifting over, and you get the same vector in terms of the inner ear signals. And the way to resolve that is by the product of your rotation that you've made over time with gravity. So again, a product code. But there are other cases where the code is going to be more complicated. So if we had a product code, a quadratic code, how would we think about decoding it? So we imagine there's some stimulus SZ, and it appears as observables SX and SY. And each of those is linearly encoded by some population of neurons. So one thing we could do is do what we did before, which is just decode those guys linearly, and we have some estimates, S hat X and S hat Y, and we just multiply the estimates. Well, the brain's not going to do that, but what the brain might do is instead of decoding first and then multiplying, it could multiply first and then decode, and that's mathematically equivalent. Okay, so we just define a new population of neurons that's a quadratic function of these distributed codes before, and then we just apply the same, we just substitute in what that S hat X and S hat Y were. Those are WR and WR, just a little transformation here, and we see that this is a linear decoding of the downstream neurons. This is not surprising. What I've done is I've taken a nonlinear code, chosen the right nonlinearity, and now we have a linear code. That's great. And then we have some synaptic weight. But we're interested in these neurons here because we haven't figured out how the brain decodes this stuff yet. So what would this look like if we were looking upstream of where the linear code was? Well, instead of having, now the correlations are going to depend on the stimulus, right, in the way that I described with the XOR case. And that's because we're going to take a product code, and that product is the thing that encodes the information. So if you pick a different stimulus, you'll get a different covariance matrix. And as you change the stimulus, you could smoothly move between different covariances. So what we often think of as noise, in this case, is actually the signal. So now we can use this expression that I wrote up before, which was for linear choice correlation when you're decoding things optimally. And I can just make the substitution of the fact that I know that this neuron R, which linearly encoded my stimulus, was a product of nonlinear coded stimuli in these little r's. And now, instead of having a ratio of population thresholds to this capital R threshold, I have a ratio of the population threshold to the threshold of this product. Okay? So this is like a trial-by-trial correlation that contains information both about the stimulus and about the choice. And we can define that threshold precisely. So let me just set up this table which shows you the comparison between the linear and the nonlinear case. In the linear case, the response was one neuron's firing rate, let's say. And in the nonlinear case, it's a product. In the linear case, the signal was the tuning of that neuron, or let's say if we're doing a fine discrimination, the way that tuning changes with the stimulus. Here it's the change in the covariance. The noise was the covariance in the linear case, but now in the nonlinear case, the noise is the covariance of the covariance. And the information can be just written in parallel to all that. So does this work? We have this test. We can say if you're doing optimal nonlinear computation, you expect that the threshold for a product of two neural firing rates is going to be equal to the amount that it predicts the choice. Well, that's what we have here. So this is data from the Valentin Dragoy's lab, where we look at the information in one neuron on the on a product, the information in a pair of neurons on the x-axis, and the amount that that pair of neurons predicts the animal's behavior, upcoming behavior. So this is a noise correlation predicting the animal's behavior. And we see that in area V1 and in V4, we see a nice relationship here. There's a lot of noise because these are difficult measures to take, but it's still very significant. And so I think it's just funny that this is a correlation between correlations of correlations. This is going to be a hallmark of any time you have higher order statistics that come from natural images. Let me just unpack that a little bit. The last correlations is the fact that we're using a nonlinear code, right? So we're taking products of neurons, and that means that their noise correlations are encoding the signal. The correlations of those correlations, well, does that product contain information about the stimulus? Is it correlated with the stimulus? Is it correlated with the choice? Those are two possible correlations of correlations. And those are correlated. There's a significant relationship between them. So there's a significant relationship between the amount that a nonlinear code predicts the choice and the stimulus. So this is something which is useful. We're going to test it better with a stimulus that's designed more to look at these nuisance variables and product codes and more nonlinear codes. And then we can generalize it too. There's lots of interest in more complex codes that's not just quadratic, more nuisance variables, maybe something deep, something recurrent even. And then we can construct a general nonlinear decoding test given some sufficient statistics for this task of interest where the choice correlation for some subset of neurons, you have a distributed code, you're only going to pick out some of those neurons at a time. The threshold for that subset is going to tell you how much that correlation, how much you can predict the choice. And it might be hard to know R, but there are ways to use other kinds of sufficient statistics to test whether this brain is using things optimally given what it's got in terms of sensory information. So to summarize, nonlinear population codes are crucial for natural tasks. The stimulus is encoded in higher order statistics of the neural responses in this distributed manner due to nuisance variables. And so we can define a new measurement which I call nonlinear choice correlation, and a simple test for when this tells you about optimal nonlinear decoding. And so we don't have to record from all the neurons in the brain. It would be useful to do, but if you collect the right neurons, even if you don't get all of them, if you get some smattering of neurons that encode at least the different pieces of information, some fraction of the total information that you'd need, then you can figure out whether the brain is doing a good job. And so this can help us figure out what parts of nonlinear computation is important and what is not. So for example, if you find that some parts of the brain are doing optimal nonlinear computation, you might say that there's selection pressure, that it has to do a good job on those tasks with those stimuli. But if you find that the brain is really suboptimal, then you say, okay, well that's not the principle, that's not the important thing for the brain. Let's focus on something else that's really important for the brain. So, thank you very much. This is the work done by students in my lab, Tianli and Raj. And also the linear stuff was done with my collaborators, Alex Pouget, Greg DeAngelis, and the data for the linear stuff was from Dora Angelaki's lab, and the nonlinear stuff from Valentin Dragoy's lab. And thanks for funding, and thanks for you, and thanks for the invitation.